No, it opens.
Okay. All right. Let's see. All right, so I'm just going to attempt to record it using my computer. It looks like the volume's kind of quiet, but I tested it before, and hopefully the volume will work, and if not, then people will just have to deal with it. Okay, so what I was going to do is kind of like, I have the Revel assignments open up in front of me, and I was just going to kind of go through and quiz you on it, just ask you guys, like, what is this? What is that? And then just kind of see if you where you guys are at, like if you can answer all the questions, or if you're looking at me like, what are you talking about? Then you have a lot more work to do. Okay.
It's a review. It's okay.
So let's start. Everything.
Okay.
Okay.
We
All
gotta
right.
fix that.
Okay. Thanks. I'm also recording the review.
So I should make a button noise.
So you should chew. Yeah, you should chew the nuts as loudly as possible. Okay. All right, so the exam's on populations. Stop! Oh my, are you serious? All these students are going to see this.
I'm a child.
That's Dr. Tupper. He teaches zoology.
Take my class. It's
Don't
awesome.
take that. Gross. Actually, I'm going to keep these for later because I'm a squirrel. Okay. All right. So, look, you almost had a student with your food. This is what happens when you're trying to buy a house and you're going insane with financial documents over there.
Mm-hmm.
Okay, so it's on populations and communities and then ecosystems and biomes. Don't make the mistake of just studying the biomes because I have students that do that. And that's only a quarter of the material that's on the exam, right? Okay, so don't expect more than like 10 of the 30 questions, more like 8 of the 30 questions to be on biomes. Okay, so let's start with populations. Somebody described to me the difference between exponential and logistic growth.
So exponential growth is like it grows and the population grows as well, and then logistic growth is where it grows but it stabilizes to a certain point.
Okay, and in exponential growth, how does the population growth rate change over time?
It remains the same.
Yay! That was a trick question. Okay. All right, the population growth rate remains the same. So the population growth rate could be like 1%, and every year it's 1%, but the effect is going to make it's called a J curve, like a J-shaped curve. For you guys, like this. Okay? In logistic growth, the growth rate will slow, and eventually the population will level off at a certain level. Okay, what is that level called, where it levels off and becomes stable?
Like stabilization or something.
Stabilizes.
It's abbreviated by an uppercase K.
Sounds like.
Some sort of capacity.
Carrying capacity?
Yeah, the carrying capacity. Okay, so you're at the carrying capacity. Okay, that's what limits populations. And all populations have a carrying capacity, even the human population. The question is just sort of, when are we going to hit the carrying capacity? Are we already approaching it? Probably. Okay, like at the end of the semester, we're going to do a whole chapter on human populations, and we're going to see that globally the population growth rate is slowing down. So hopefully we're hitting a carrying capacity. So what are some of the limitations that could cause that carrying capacity to occur? Like what limits a population?
Invasive species?
Like, yep, an invasive species could do it. What else? Yeah, humans. Yep. Yeah. How about less? You guys are thinking of like really extreme things.
Extinction.
Hmm?
I was going to say extension.
Extinction? Well, yeah, that would be like a carrying capacity of 0.
0.
Yeah, like we literally can't have any of them. So what about just simple things like hiding spaces, amount of sunlight, amount of nutrients, okay, the number of predators, communicable disease, the amount of food, water.
Like the biocontrol?
Yep, so there could be, biocontrol is more about one technique to control invasive species. So I'm talking about there's like physical and there are biological limiting factors. Okay, so the physical are the non-living things. So something like for a plant, access to sunlight, right? So you can only a certain number of individual grasses can grow because at some point they can't all get to the sun. And then biological is the living stuff. So you can't have 10,000 rabbits because there's a fox here, and the fox is going to start eating them if there are too many. Okay, so there are physical ones and there are biological limiting factors as well. And the only difference is just, is it a living limiting factor or a non-living limiting factor?
The biological one is like where like the plant can't receive sunlight. Is it living?
That's non-living,
That's
because the sunlight is not living.
Okay, and then for the biological factor, that would be what example again?
Like predation.
Predation? Okay,
Mhm.
when the predator needs to prey.
Mm-hmm. Okay. All right. Okay. So what would be a good definition of a population?
Like a group of animals living together amongst each other of the same species?
Yes, of the same species. That is important. Okay? So it's like the white-tailed deer population in Rock Creek Park. That's a population. So it's a group of individuals of the same species living in the same place at the same time. I mean, that's kind of, you don't really need to add that there. Okay? How is that different from a community?
Communities where they're different species, but they live in the same community.
Yes. Yeah, so it's multiple species interacting with each other. Okay? And then how is that different from an ecosystem?
Ecosystems like the environment where they live in.
Yes.
Surrounds the population of the animals.
Ecosystem will include everything, like
Yes.
plants, living animals, the environment.
Okay, yeah, what do you mean by the environment?
It's like their
The-
homes.
Yeah. Okay, so that includes the non-living things too.
Thing, yeah.
Okay, that's like the water. I mean, when we're talking about biomes, that's just a way to classify ecosystems.
That includes even the weather condition, right?
Oops. What's this? Yes. Yeah, so the ecosystems including the non-living parts. So you're kind of like zooming out in your scope, right? Like just the white-tailed deer, all of the community of mammals in Rock Creek Park, and then the entire ecosystem of Rock Creek Park, right? The mixed and broad, what do they call it? Temperate, broadleaf, and mixed forest. Okay. All right. If you were to write an equation for population growth rate that includes stuff like birth rate, what would the equation be?
R equals parentheses.
Okay. So
Is it birth?
R, yeah.
Plus immigration rate
Yes.
minus death rate plus
Emigration. Yeah. So births plus immigration, things that are being added to the population, minus deaths plus emigration, things that are leaving the population.
And that is, what is the term for that?
Population growth rate. Okay, so it's like the simplest way to calculate a population growth rate. And really the key is just knowing the difference between immigration and emigration, because we know what birth and deaths are.
Immigration's out, immigration's in.
Right, immigration, someone is coming in, emigration, somebody is leaving. Okay. All right. Let's see. I'm just kind of looking through the Revel assignment. Okay. R-selected traits versus K-selected traits. So one trick to remembering the difference is that R-selected, that little r, that means population growth rate. And K-selected, K means carrying capacity. So the R-selected traits are ones that are optimizing growth rate, and the K-selected traits are ones that are sort of trying to keep the population steady around carrying capacity.
One more time for the S selected.
R. R-selected versus K-selected. Yeah, so the R-selected ones, it's a little r, right, a lowercase r, and that's population growth rate. So those are traits that are, for that species, they're trying to maximize the growth rate. And for K-selected traits, they're trying to keep that population right around carrying capacity, keep it nice and stable. And of course, these plants and animals, and we'll just talk about animals, it's a little easier to do that. They're not like trying to do anything, right? The termite's not like, I want to maximize growth rate, I'm going to have 1,000 babies. Like, this is just what they've adapted to do. Okay, so what's the difference? Or you can give me an example. Something R selected, something K selected.
Like rabbits, they
Mhm.
have a lot of babies at once.
Mm-hmm.
And like a panda would be S selected. They
Okay.
have one baby.
Why do you keep thinking it's S? It's K. Maybe it's because you're thinking in logistic growth it's an S-shaped curve. I don't know.
Wait, so the R selected is which one?
The R selected is the rabbit.
Okay.
I don't like the way your book says R selected species because the rabbit having lots of babies and being able to have lots of babies over and over again, that's R selected. But caring for the babies, that's K selected. So I don't like how they say R selected species, K selected species, because it's kind of lumping, it's saying that it's,
Is it R and S?
R and K.
R and K. Oh my gosh. Why is it
It's a good
S?
thing it's multiple choice.
I was like, why was
There
it?
I don't know.
S?
There
I
won't be
don't-
anything in there that says S.
I wrote SM for a second.
So R,
No.
so R selected is, like sexual maturity, very young, having lots of babies, very little or no parental care, having babies over and over again. I mean, usually these species, it's like as soon as environmental conditions are favorable, like as soon as the spring comes, right, or as soon as a food resource is available, they crank out the babies. The strategy is just to have as many babies as you can as soon as the resources are there, and then you just hope that a few survive. Right, so that's very unlike us, right? We're very, very K-selected.
K selected
Okay.
would be like panda.
K-selected is like pandas.
Okay.
It's like most large
Like bears.
mammals are like K-selected. Yeah, so that's like having very few babies, lots of parental care. I mean, our own babies can't even walk until they're a year old, right? So they need a lot of care to survive. And it's not like one strategy is better than the other. That's just how different species have adapted to survive.
Mhm.
Okay, so that's R and K selected. Okay. Let's see where we are. All right, we've already talked about carrying capacity. Okay. All right, so if a carrying capacity is exceeded, right? Like if you put, I think we had a group activity where you had to think like you're grazing sheep in an area, and what would you do to increase the carrying capacity? And so, what usually would happen is you're grazing too many sheep, they eat all the food, and then what happens? There's no more food, okay? And so what happens there is called a state change. So basically, the sheep have destroyed the field. Okay, you can know erosion's going to occur, you can no longer graze there. So sometimes if carrying capacity if you go way over carrying capacity, sometimes the population can sort of come back down and get back down to carrying capacity, things will be okay. But if it becomes too extreme, like you eat all the food, for example, then something catastrophic can happen. That's a state change.
So you can say if carrying capacity exceeds too much, state change will occur.
Yes, yeah. Okay. So now let's take a look at communities. We've already defined what a community is. Okay. Let's talk about energy flow through a community. So we can organize community into trophic levels, right, with the producers at the bottom, then the primary consumers, secondary consumers. Okay, and as you move up through the trophic levels, you lose a lot of energy, right? This is called the rule of 10. Does someone want to try and describe what the rule of 10 is?
It's where you use like 10%.
where you use 10%?
No, you said 90%, 10% left over.
Yeah. So you're going to, so only about 10% of the energy at each level makes it to the next level, right? Where does the rest go? I mean, there's lots of places it goes, but most of it is lost as heat. It's just used as metabolism, right? Like every single calorie you eat doesn't go towards making a bigger you, right? So like every single calorie the bunny eats doesn't go towards making a bigger bunny. So when the fox comes and eats the bunny, he's not getting all of the calories the bunny's eaten. Okay, so he's only getting about 10%. So how does this explain why you can only have a few individual top predators in a community?
Have too many predators?
Why can we only have a few? We might. Why can we only have a few top predators? We might see 1,000 rabbits out there, but we're only going to see like one fox.
Because like if you have too many predators, it'll eat every little like species afterwards.
Well, yeah, because there's not going to be enough energy. By the time you get up to the top of that pyramid, there's not enough energy left. That's why we're going to have millions of individual producers out there, and then thousands of herbivores, and hundreds of mesopredators, medium-sized predators, and maybe like one coyote or one bear at the very top. Okay, because you're losing energy. Okay, so that's called the rule of 10, and the trick is really just remembering that only 10% makes it to the next level, not 90%. And it's tempting to think, because it seems so wasteful, right? Like only 10% is making it, but that's actually what's happening. Okay, so in a community, you just mentioned a keystone species. What is a keystone species?
Species that has a disproportionately important
Right, exactly. So give me an example of one. The starfish, that's the classic example, yeah. That's the one I learned, right? It's like the most classic, because it's the one where the name keystone species came from it, yeah. Okay, I think your book also gives an otter as an example, and then I just moved away from the page, but what else is in there? Oh, the salmon. That's a really cool example of a keystone species, because it's not just like it provides food for bears. It's like it provides food for a whole bunch of different animals. So then it comes into spawn. And then the dead bodies of the salmon, because they all die en masse after they spawn, provides nutrients for all the plants. And the animals that eat the salmon, they walk away from the stream, then they poop somewhere. They're basically taking nutrients from the water and moving the nutrients away from the stream. So they're providing nutrients for plants really far away from the stream too. It's a really cool example. Okay, what about resistance versus resilience?
So resilience
You were ready for that one.
because I've been studying on like the rock.
Good. Good.
So like resilience is like what can live afterwards, like as a disturbance. And then resistance.
But what do you mean? Wait. Resilience is after a disturbance. What happens?
No, resilience is like what is like live after. No, resistance is what can like live after like a disturbance.
Okay. Keep going, because you're
like,
kind of close.
Resistance can withstand the tolerance of something happening to this like environment, and then resilience is like what you can make up afterwards. Yeah. Resistance is it's resisting change. Like a disturbance can happen, and the ecosystem or the community rather is not really affected by it. And the resilience is it bounces back. There you go. I was like,
yeah, it can bounce back. So like the forests around here are pretty resilient. Like they're pretty good at bouncing back after a disturbance comes through. Somewhere like a tropical rainforest, not great at bouncing back. Okay, what about primary versus secondary succession?
Primary is like when the first animal they're introduced and it colonizes the first like location, like the environment, and then like secondary succession is like when there's not like a disturbance where some life is taken away but is able to live like the second generation of like the environment.
such?
Exactly. So primary, you're starting from nothing. Secondary, there's something there, but it's been very much disturbed.
Like the what you said with the forest, if you were like the one with it was like a street
Mm-hmm.
and they had poor soil, and you said if you were to take all of the soil, that would be primary just because
Yeah, it's totally dead underneath. Yep. Yep. Yeah, you're pulling up asphalt that's been there for like 40 years. It's totally nothing is underneath there. That's primary.
The secondary would be like the forest. If you were to take it away, there would still be some life
Yeah.
still there to
Yep.
make up for what was lost.
Yep. You cut down the trees and then you leave it alone and you come back in 40 years. It's going to look a lot like the forest that was there 40 years ago. For some forests, like in this area, yes. In the tropical rainforest, probably not.
So primary is what you starting from nothing.
Yes.
And secondary. How would you like sum that up?
Well, there's still life there, but when there's like taken away, there's still some like leftover plants and other species that are left over
Yes.
from the wipeout of that generation, where they're still able to live off and continue that second generation of the secondary succession. That happens amazing.
Okay. All right. Let's see. Do like, we're perfect for time. We'll do like 2 more concepts for this. And then I'm a little worried that this recording a video on my computer, that it's gonna freak out if I make the video like an hour long. So I'm gonna make it in 2 parts. Okay. What's the difference between a non-native species and an invasive species?
The non-native is like the snakes in Hawaii, where it's by accident, it was unintentional. Wait, what? That's invasive, right?
It depends. I don't know.
Yes, it is. Wait. Wait, no.
What do you think
Common basic.
Yeah. So what do you think a non-native means?
Something that was brought in that's not part of it.
Yeah, it doesn't matter how it got there. It could be accident.
What was the question?
What's the difference between non-native and invasive?
I have written down invasive species and native species. Should it be non-native?
No, there's native as well. I'm just asking you those two.
Native species like where the species was born and brought up. And
That's native, yeah.
And then non-native,
Someone has money,
it
goes
was
to
like
Africa,
brought in by accident.
buy something, sneak it into the US.
I'm just thinking
Uh-huh.
like the snake.
Now, so if it comes in, if it's not native,
Like maybe because of like a climate change or like some kind of reason, like for like the birds that you talked about that all died off, like they had to like migrate because I forget why they had to migrate, but because they had to migrate, like I don't know, they weren't. It's not like they were non-native, I guess, because it's not really good.
yeah, if they're not causing a major ecological disruption, then they're just non-native. They're just. Would you, Dr. Tupper? What's a good example of a non-native species that's not invasive? Or are you so extreme you can?
Earthworms.
Earthworms?
Yeah.
What about are sliders? Are sliders non-native?
Mm-hmm. To
here.
To here.
But they're not. They wouldn't be considered invasive.
No.
Yeah. Okay. So like a red-eared slider, like a kind of turtle, they're really common.
I guess it depends on who you ask.
I know. Yeah.
Wait, is this, what is this like? Yeah.
A red-eared slider is a turtle. You'll see them all over the place, but they're non-native. But most people wouldn't consider them invasive. It's not. Yeah, because they're not causing a major ecological disturbance.
They're unintentional.
It doesn't matter how they got here. It's just a matter of how disturbing they are. But if it's something like the kudzu vine or English ivy that's completely growing out of control with like no animals are eating it and it overtakes all the native plants and within a few weeks it's totally covering up the side of your house, that's invasive. So it's just a matter of degrees. Right? So it can be non-native but not causing a huge disturbance. But invasive is like the examples that are in your book, like the brown tree snake in Guam, like these really extreme, very disruptive introductions, whether accidental or not.
That was the mixing into it.
Yeah. So then, what's an endemic species?
Species only found in one place of the
Yes. Okay. So what's an
A
example?
frog in a rainforest.
Right, like it only lives in that one little patch of like cloud forest at the top of a mountain in Costa Rica or something. Yeah, exactly.
So non-native has nothing to to do with like where it came from.
It does. It means it
just
doesn't. It's
means
not
that
native to
they're
that
not
area.
disturbing.
Yeah, naturally it doesn't occur there. It got there either because someone put it there on purpose
It's
or
not causing
accidentally,
an issue.
but it's not really causing a problem. Yeah. Okay. Let's see. What else do we need to do? Okay. So now let's go to the next chapter, which is ecosystems. No. Yes, ecosystems and biomes. Okay, so we'll end this first video and start